existing data. They provided some data online, and they wanted to see if anyone could actually improve the performance of the recommendations by minimum 10%, and you would get the prize, right? There's this guy called Geoffrey Hinton, and he effectively is dubbed as the godfather of deep learning, so you can Google him as well. Moving on a bit to the more recent times, there's mention of AlphaGo. So AlphaGo was actually developed by Google's DeepMind subsidiary. It actually beat, I think, one of the world's best players at Go. And in terms of the scale of this, right? So if you look at chess, right? Chess actually has, I think, in terms of the number of possible combinations or moves, right? It has 10 to the 111 possible combinations. And I think if you do some filtering there, you get 10 to the 40 or somewhere there, right? Go actually has 10 to the 170 possible combinations, so it's much more intense in terms of the complexity. And just to put it into perspective, I think our observable universe, forgive me if I'm wrong, it contains, I believe, somewhere between 10 to the 78 to 10 to the 82 atoms. So the number of possibilities in Go is more than the number of observable atoms in our universe right now, or at least in the observable universe, right? So that's just to get an idea of how, computationally intense, trying to do some machine learning on this was. I think they used, if I'm not mistaken, 1900 CPUs cores to do the computations, as well as 280 GPU, devices to assist with computation for the AI that ran AlphaGo, right? So very interesting, right? So you'll see here that I have two white lines in the timeline here. The first one is Apollo 11, and the second one is TI-84, right? So I'll go on to the next slide. So TI-84 is a calculator developed by Texas Instruments, and you have to the right there on the screen the onboard computer for Apollo 11, right? And the TI-84, this little calculator, is actually 350 times faster in terms of processing than the Apollo 11 onboard computer. Just to put it into perspective, how powerful how powerful computation actually got between just simply 20 years, right? It increased exponentially, and you'll realize here that initially in the timeline here, it was more definitions, just not definition ready, but more like formulations and ideas on AI, the perception and so on. And then go down to the later parts of the timeline, in recent years, we've seen that these things actually have now been implemented because of the increase in, or the availability, I should say, in computing power, right? So just to put that into perspective, right? This here is Margaret Hamilton. She was actually the director of software engineering at MIT Instrumentation Laboratory. And this lab, I believe, was hired by, I think, I'm not sure if it was NASA or whoever was doing the Apollo 11 mission. And she was effectively, the director there, and she was hired through the lab to write the code to launch, the mission to the moon. It was approximately 145,000 lines of code, and it was written in something called ACG. I think it's Apollo Guidance Computer, some specific language that they had. But to the right there, you'll see that there's a stack, and that's how much code she actually wrote, or that was developed for the mission, right? And again, it ran on this little thing that's 350 times less powerful than a calculator, right? So just to give an idea of how far things have progressed, right? So bit of the history aside there, and a little definition of machine learning. So let's get into something of a problem actually here: email spam classification, right? So how do you know the email is spam, right? So I have an example listed here, and I have the reference software I got from Google just for plagiarism purposes, right? And in the example listed here, they have highlighted some instances of the email that kind of pointed towards that as spam, right? So first thing, you got instructions to delete your account. 24 hours, your account will be lost. So that firstly, there, the first thing you could realize is that they're kind of making a panic, and then you get a link, number 3, that if you click it, will take you to some site. Probably have to log in, and then from there they would obtain your password and username and lock you out, and the whole scenario of trouble begins, right? So that's one example there. Another example here is actually a case of Outlook, where firstly there was a fake domain being identified as a threat, saying that something happened, features will be turned off. Typically with spam emails, you get spelling mistakes sometimes, you get grammatical errors, and you also get a fake email signature as well. So I mean, it doesn't happen all the time, but there might be there, right? So excuse me, now we have these two instances here of what spam might be. How do we construct or approach the problem, right? So just to put it into perspective, right, as of 2018, spam accounted for 45% of all emails sent, right? And that same year, 14.5 billion spam emails were sent out every day, right? And for every 12.5 million emails sent, one person actually responded to it, right? And lastly, over a third of spam emails actually are from forms of advertising. So just a bit of an idea of how, difficult or how widespread the problem of spam actually is, right? So your email clients, Outlook and Google, etc., have spam filters built in that, could determine if your mail actually is spam or not, with a high degree of accuracy, I should say. Right. So before we get into machine learning, I'm going to introduce one approach, right? And it's a very simple approach. It's just called a rule-based approach, or effectively our rule-based system. And we're going to compare it just now to a machine learning-based approach, right? So I'll move on a bit here. So the rule-based approach, right? So in order to get this approach to work, we need to firstly identify parts of the email and then determine whether or not it should be classified as spam based on whatever that particular segment of the email contains, right? So let's try and pay particular attention to the sender's email address. We saw there the body of the email. You might have the mention of unbelievable offers. There might be links to reset your password or sign in. Pay attention to the subject of the email, right, and so on. So that's just a few things to look at, right? Now, just simply think about how much rules you need to create for all these scenarios. So for those of you in ComSci, computer science, and so on, IT, right? If you just look at these two examples here, the first one, right? A very simple way of saying is that, okay, if the body contains your account will be lost. Say it also contains your account has been locked or whatever, right? You have to manually put that in a series of statements that will be checked on the email itself to see if it contains these things. And if it does, then okay, it's flagged as spam. So what if now, something changed, right? So just say that the text changed from your account will be removed or locked from your to your account is going to be deleted, right? It's two different ways of saying the same thing, and effectively in our rule-based system, there's no way of saying okay, these two are the same. You need to input it twice, right, to mean that it's spam, right? So you'll see very easily here that there's going to be a lot of rules you need to create to kind of cater for all possible scenarios of spam, right? And here we get onto the limitations of the rule-based system. So actually, for like emails and stuff, spam-based classification, there might be hundreds or even, I would say not even hundreds, probably thousands or millions of variables required to make a decision, right? And as you have these large number of rules in a system, right, it's going to become very difficult to manage and update these rules, right? And that's going to make your scaling very poor, right? Secondly, any additional constraints or exceptions might actually make things even more complicated, right? And thirdly, if you were to try to achieve intelligent behavior, right, it's quite often limited. And this is because we don't actually know what's going to happen in the future unless we see examples, right? So is a bit of a reactive based approach, right? So only when you see something new coming up as spam, you could actually make a rule for it, right? It's very much reactive and not proactive, right? Okay, so here we now actually onto machine learning and where the benefit begins, right? So here are some very simply defined advantages, right? So ML systems are easily scalable, right? So as things change, the system can adapt easily to the change, right? And in terms of scalability, it's quite often very much easy to scale, right? In terms of the second point, you'll realize that with these systems, there's no need, sorry, to explicitly program or write forcibly rules for the system, right? It learns for itself based on whatever is thrown at it and is able to again, as in point 3, as we can see here, it is able to adapt and evolve over time, right? Okay, so while machine learning is perfect, it is very powerful, it's good. There are some things that you need to know or keep in mind when doing machine learning, right? So it's not the holy grail, and often at times there are some caveats, right? So the first thing is that probably heard of the term garbage in, garbage out. So data that is of poor quality often results in poor performance, right? That's one. So you could have the best algorithm out there. If you don't have, quality data for it, it's gonna pretty much often result in not so ideal performance, right? Um, Many machine learning models tend to require large amounts of data. So that's the next thing. And the thing is too that, sometimes when you're doing machine learning with large amounts of data, you need to label your data, right? So actually, you need to have actually like an expert in the area go through and actually say, okay, given this piece of text here, this might be classified as spam. True. Given this text here, this is not spam, false, and so on. So there's initial work that needs to be done upfront, but once it's done and it's put in place, it actually makes life a bit easier, right? The third point is very important, and it's the point of interpretability. And this could actually determine whether or not the model will be placed on a shelf or actually be used in a real world scenario, right? So, like in Guardian, like if you were to implement a neural network per se, it's a very much considered like a black box. So in some cases, you need to define approaches and have methods to actually investigate the model and say, okay, the model picked up the signal from our data and translated back to the business. So that point of interpretability and explainability actually is important. So in a business context, you need to be able to say, okay, the model was trained, it learned something, but where did it pick up the signal from, or what features it learned from? So there's a bit of an area that needs to be kept in mind when you're doing machine learning, right? Unfortunately, machine learning is stochastic, not deterministic, simply meaning that it's probabilistic in nature, right? So the output would change, based on your input, and it can vary over time, right? It's not set in stone. Okay, so some examples of machine learning. So typically, I mean, you'll probably have Netflix, and Netflix uses machine learning heavily, as you can see from even since 2006, with their movie recommendations. With regard to Google, a lot of their services have actually machine learning embedded into them. So Google Maps, photos actually, I think now could actually identify faces and tag you in your own pictures and tell you your friends in your pictures and so on. Google Search actually uses machine learning. Amazon, typical stuff, product recommendations used heavily throughout Amazon. Facebook, the AI machine learning systems are used to process your photos, videos, and text. And I just say your photo probably contains some text about a dog. It might recommend, that you buy some pet food or something, So just to see how powerful these systems actually are, and some examples of them, right? Moving on a bit, some statistics on machine learning. So actually, let's get an idea of how big is actually getting right now in terms of the globe. $13 trillion was actually the potential anticipated economic activity that AI could deliver by 2030. It's a study done by McKinsey, and same company McKinsey, a study in 2020. 50% of the respondents said that the companies are actually adopted AI in at least some or minimum one business process, right? With AI adoption, you're going to increase revenue. And for example, 80% of companies or people said that AI actually helped increase revenue, right? To the medical side of things, Google actually had a lung cancer detection algorithm, a machine learning model, outperform actually 6 human radiologists. So just to get an idea of how good it's getting. And AI, as you know, very popular job nowadays. And the field of AI, the job's actually now the second most in demand job, based on some 2020 study. So again, it's becoming very popular. It's very involved, and it actually pays pretty nicely once you get pretty good or involved in the field, right? So moving on a bit now. We're going to get a bit now into the deep dive here. And this is where I'm going to explain some, basic concepts of machine learning. Nothing too detailed or anything, but just to give you an idea of what's going on in a high-level scenario. and then we'll step onto the actual lab itself, right? So I think before I jump onto the lab, let me just send you the link, right? So I think I have it in my browser, right? I'll send the link here so you guys could actually, you guys can actually just open up the link. And I think once you have access to a Google account, you could actually open up the service called Google Colab. Colab actually is an online instance where you can actually, um, write code and investigate stuff for some data sets online on your browser, right? So nothing needs to be run on your machine. Everything runs on the cloud, right? It's free to extent and you can't pay for it. I think the free instances last between, a few hours to up to 12 hours max. And if you pay, you get more runtime, continuous runtime, you get a faster GPU and so on, right? But back to the slides. Just give me 1 sec. Okay, so before I go to section 3, any questions so far? Anything you want to bring up, any topic you found intriguing of it so far? Trying to make it a bit interactive here. Right, I guess we'll move along. Right, so dive into machine learning. Right, so fundamentally, machine learning models, and I mean this is a fundamental scenario, this is a very abstract, there's a much deeper level of breakdown as you get deeper into the field, but fundamentally, you can think of machine learning models as being unsupervised or supervised, right? So in terms of supervised learning, that's where we use labeled data sets. So in the case of spam classification, it actually falls under supervised learning, right? Why? Because we have the emails, sorry, right? Can I be spam or not? And we have also as well data that indicates that the emails are spam or not spam, right? In terms of unsupervised learning, this is where we deal with unlabeled data. So we don't actually have the answers to what the data actually is, if it's either spam or not, if it's true or false, if it's good or bad. So what this does is that it uses techniques, right, or algorithms that tend to group data based on similarities or differences. And this is known as clustering. And there's also the fact of getting into, unsupervised learning a bit deeper. And this categorization is actually dimensional reduction. So this is actually taking that data that you have and somehow condensing it in a form that reduces the number of features but preserve the original structure, right? So that's unsupervised learning for you. And in terms of supervised learning, there's the issue of the subcategory of classification and regression, right? So classification, it says here that the output of the model is actually, mapped to discrete values. So true or false, yes or no, spam or not spam, breast cancer or not breast cancer, right? In the case of a regression problem, right, the output of the machine learning model is assigned to continuous value. So let's just say we want to predict the price of a house given some data. So we have the age of the house, the square feet of the house, number of occupants. We could try and predict the price of the house. This here actually is a regression problem. And like the spam instance or the spam problem is actually a classification problem, right? Okay, moving on some more. All right, so now let's try and very much in a very abstract scenario compare a machine learning approach versus a rule-based approach, right? So which one do you think is a machine learning approach and which one do you think is a rule-based approach? Anybody?
Can you hear me?
Pardon?
Just wondering if you can hear me.
Yeah, I can hear you.
I would say the second one is the machine learning.
Okay. I won't say if it's correct or not as yet. I'll give
Oh.
other person's opportunity to answer. So if it's machine learning, actually no. If you think it's machine learning for one, put A in the chat. Okay. Jeremiah says A. So A for machine learning, right? Michaela and Beverly. Okay, cool. And so A means, I'll say it again, right? A means that you think that the first, the first chart here, this first line here, actually, with these three flows here, they say that this means machine learning, right? Anybody for the second one? So does the second one mean machine learning or is it rule-based? So for those of you who think that the second one is machine learning, put B. Okay, some of you all put A and B. All right, so let's try and go back to this side and see what the answer is, right? So I don't want to tell you the answer. Let's go back a bit. So, all right, so you realize that with rule-based systems, right, you have to manually construct the rules, right? And as defined by machine learning, right, it actually is able to take your data, right, like it's supervised learning, and in the case of supervised learning, it needs to be labeled, right? So again, in the case of spam, I have the information from the spam. I have the subject, the body, the domain it came from, and so on. That is my input data. I also have the output, right? So if it's either spam or not, or the target, as they say, right? So given that information I just reiterated there now, which one do you think is machine learning now? Is A machine learning or is B machine learning? Right, so for those of you who said that, A is machine learning, right? We have the input, we have some rules that you're going to construct, and then based on the input and the rules, if the inputs are satisfies the criteria for the rules, right? It's going to be either classified as spam or not, right? So that's one flow there. Then we have the input. Input in this case is going to be like your, say, the age of the house, the number of persons in the house, the square feet of the house, right? The output here now is going to be what? The price of the house, right? And that now is going to map to rules, right? So effectively, the answer is B. B is the machine learning approach, right? And again, to get a bit more into it, is that the model is actually going to take your data, and this is in the case of supervised learning, right? This categorization here, right? It's going to take your input, which is again your age, potentially number of persons, square feet of the house, and it's going to say, okay, given these values here and the answers for them, I could actually try and construct rules for myself, right? And use that now for the future. So again, the second flow here denotes what machine learning is. It takes your data and the answers for your data, if it's spam or not, the price of the house, whatever, and tries to construct rules based on an algorithm and mathematical approaches, right? The first case here actually is the instance of the rule-based approach, right? So you have your input and you have your rules. If the text contains, your Facebook account is now locked, that is a rule there. And if your input matches your rule, you get the output. Okay, this is spam, right? So anybody confused there? And you'll understand why A is not machine learning.
I understand.
Okay, cool. Right.
I have one question.
Yeah, sure, Jeremiah.
Regarding the first one, right?
Mm-hmm.
Would that mean that would be like unsupervised learning? That wouldn't be classified as unsupervised?
So unsupervised, actually, so back to the study. So what it does, right, is that it groups your data based on similarities and differences. So it doesn't really construct rules, right? Because how I could explain this, right? So let's just say, all right, that we're dealing with cities in America, right? So the distance between each city, we have it listed out there, right? Versus cities in Trinidad, right? Now you're saying here that we want to try and let's just say that, let me try and find an example here for you. Okay, so let's say we had cities, right, in America and Trinidad, and we had, let's just say, the distances between a set of cities in Trinidad and a set of cities in America, right? Now you're saying here that clustering on supervised learning, you could say the categorization fit, right, could be considered the first one, right? Now, again, in terms of the rules, right, what is meant here is that you need to specifically define the rules, right? So with unsupervised learning, right, there's, again, so with machine learning, right, there's no specification of rules per se, right? Based on the algorithm you use, whether it's unsupervised or supervised, the model is going to learn for itself, right? So in the case of just saying we're going to apply a clustering algorithm on the distance between cities in Trinidad and America, what might happen is that it's going to realize that the distance between cities in Trinidad are much smaller than the distance between cities in America. And because of the distance being smaller now, it's actually going to create rules for itself, within the model based on the maths and statistics, and give it that separation there. So there's no there's no formal definition of you actually saying, okay, I am specifying the rules. So I should actually mention here, and I'll make an update to these slides, that this is hard-coded rules, I should say, right? So that's one fix there. I should have made to these slides. But do you understand what I said, right? That based on your data, it is able to adapt it, right?
I have one clarifying question.
Sure.
So basically, rules are patterns in a way.
Yeah, so in the case of the machine learning context, rules are patterns that the model has learned. And in the case of the rule-based context, I should have identified it a bit clearer here. The rules are what you actually have to forcibly specify.
Okay.
Yeah, right. Okay, good. So moving on a bit. All right, so we almost get to the lab session, right? And before we get to it, we need to have some prerequisites defined, right? So firstly, don't be scared. The mention of linear algebra and line fitting, we're going to have an idea of the notion of error and loss, and then gradient descent, right? So let's jump into linear algebra and line fitting, right? So this is basically CXC match, right? So let's just recall the equation of a line, right? Y equals mx plus c, right? Y, that is the value. In this case, you want to predict, right? M is a gradient or the slope or weight. X is the input, like it can be considered the input, and C is your intercept or the y-intercept, right? So I have to write here a graph, right? And the graph has a set of data points, listed in different colors, right? And there's a line. So what we could actually do is think of the line as our machine learning model. This is a very simple case, right? And we're going to assume that we have n data points. So if we have 10, n is 10, right? So again, we have the equation of the line, we have data points here, right? And we have on the y-axis the price of the house, and we have on the x-axis the area of the house, right? So this means that given some x value, some area, we can map the area back to the price. So just say that the area was 2,000 or like 1,500 square feet, right? It's going to map to about $2 million, just per se, right? This case might be a bit off in this case here. If we have 10,000 square feet, 11,000 square feet, the price is going to be around $2 million, just per se, right? So we understand that. One step further. So what we could actually do, right? So we're going to assume that the line defined here in red, and this is the equation for the line here. We're going to assume, that the line is our machine learning model. So what this line says is that if I take any x value, say I take 10, right? I could go up, and wherever I meet the line where it intersects there, I could go straight across to the left and get the corresponding y value. Again, I could go 20, intersect, go to my left, that's my price. So we're thinking now as the line as a machine learning model, right? So again, the equation is here, y minus 6 is equal to 0.75, and in brackets x minus 8. Again, x here is your input data. That is effectively area of your house. And y now actually is your target value, or what you want to predict, the price of the house. You all understand that there? In a very simple abstract scenario. Give me a 1 if you understand. Okay, good. So again, think of the line as your model, the machine learning model, right? So now, what we want to do is actually calculate the loss or the error, right? So what is one way in which we could do this? So in this simple 2D scenario here, this simple graph here, what we could actually do, if actually the red line is our model, right? And we have some data points here listed, what we could actually do is say, okay, if I take this green dot here, I'm sticking with my mouse, right? I'll make it a bit bigger, right? And if I calculate the distance between this green line, the green dot, sorry, and our red line, we get an error. So say it's just 5 units, right? If I calculate the distance again between the black dot and the red line, error might be 3 units. Distance between the purple dot here and the line might be 1 unit, right? Now, what I could do, so given this particular line or this machine learning model, I could say, okay, I could calculate how good the model is going to perform by calculating the error or the loss, right? And what we could do actually is take the error with regard to all data points on the graph. So now we're going to sum now the observation, which is actually the actual points, which is the green, the black, the blue, purple points, right? Minus the prediction. So how do we get the prediction, right? So given that we have the line here, right, the prediction can be obtained by taking the x value and plugging it into the equation here, right? So let's just say that this x value here for the purple point here, that was, say, 1.5. If I plug 1.5 into my equation here, I'm going to get the point here, where my mouse is here on the line. Now, I can get the distance between the observation, which is my purple dot, and the point on the line here, a few units here, very small. Again, if I plug in the x value for the blue dot here, right, I'm going to get something like, say 6 is my x. So 6 now would correspond to a value of, say, about 4 or $4 million in terms of the price here, whereas the actual value is actually $8 million, right? So the distance between now, the point now, and the corresponding x value on the line now could be considered the loss. So if I sum now the loss, right, which is actually the difference between the observation and my prediction, right, and I square it now, I would get the idea of the loss if I use this particular line here. Now, what I could do is say, okay, now, let's try and use a different line. If I increase my gradient or decrease the gradient now, I effectively have a different line. And now, if I take all the data points and plug it back into the line and recompute the error or the loss now, it's going to be different. So all machine learning really is now, I'll go to the next slide now, is that it's effectively a way in which we could find now the best model or the best line per se that could best fit our data and give us the lowest loss. That's what it really is in a nutshell, right? So concept of, actually no, before I go to it, you all understand the concept now. So all machine learning really is, so after given some data, right, you're going to try and best fit your data in some way possible, and you're going to measure how well your model fits your data by some loss function. In the case, the loss function here was the distance between the actual value and the predicted value. Simply that's what it is. And because it could be either way, positive or negative, we're just going to square it and then do the sum. So that there now is the loss, right? And to determine the optimal line, we can construct a few hundred different equations of lines, pass it through the loss function, compute the loss, and then we pick the line with the least loss. Does that make sense to you guys? Give me a 2 in the chat if it makes sense. Okay, good. So you all understand. Last slide here before we go to the lab. Gradient descent. So gradient descent is a very much a popular optimization algorithm or strategy used in machine learning today. A lot of algorithms actually use it in the background, and it's based on finding the local minimum of a differentiable function, right? So this differentiable function we're talking about is the loss function, right? So effectively, we define the loss function here as this here, the sum of the square difference between the observation and the prediction. Again, the prediction, we calculated the prediction based on the equation of the line, right? Okay, so we have on the graph here now, on the x-axis, the size of the house in square feet, right? Same, I should have put area of the house, my bad. So let's just assume that this graph, the x-axis is the same, the area of the house. That's my mistake there, right? And then now, we have on the y-axis now the loss or error. Now the loss, again, as we said, it's computed based on, the creation of the line, as well as the different data points there. So now, right, we can think of gradient descent as hiking down to the bottom of a valley. So as you proceed through a gradient descent, you're gonna go in the direction of the slope, right? You're gonna go step by step by step by step. And initially, when you start off with your machine learning algorithm, your loss is gonna be high, right? And as the machine learning model trains or it learns on your data, it's actually gonna decrease the loss. So at some point now, we're gonna step down this mountain of loss, and we're gonna actually arrive at the bottom here, which is actually now the point where you have the lowest loss possible. And that is what gradient descent does in the background. So if you apply now, the approach here of finding the best equation for the line using gradient descent, it effectively now is an approach that we could use now to find, the best coefficients here that best fit our data. Simply stated. Makes sense so far, right? Give me a tree if you understand what's going on. Okay, good. I've seen one tree, 2 trees. Okay, so we get some trees. So I guess we have a fine understanding there, right? So now we're going to go to the lab, right? And with the lab, we're not going to do any kind of actual algorithm. We're just going to implement some things and see what the results look like, right? So I sent you the link to the Colab notebook. So let me just escape it here. And I'll send the link again to those of you who just joined the chat, right? So again, Colab is an online platform developed by Google to effectively do data analysis, machine learning on the cloud, right? And I'm going to share my screen here with, what's going on. So you all should see the exact same thing. I think I have an instance, and the instance actually is running. So you'll see that my one actually is consuming some RAM and disk space. And I think you could activate your environment by pressing some button on top of the top right. I think you could actually enable it here. It'll take a few seconds to initialize, and then we could actually go ahead and do the lab, right? So throughout the lab, we're going to have blocks of certain blocks in the notebook here. So this here actually is what you call a Jupyter notebook, right? And a Jupyter notebook actually is like a program that actually allows you to make comments as well as execute code blocks within the same area, right? So it's good because as you make inferences on particular investigations on your data, actually you can make comments, right? So that's what it is. It's like actual notebook. You're making calculations and doing programs, running programs, and so on, and then you're making notes. So Jupyter Notebook is the name, right? So Colab is actually based off Jupyter Notebook, and it's on the cloud, right? So what I'm going to do is that in certain cells of code, you actually see that to the left, you could actually run the cell, right? So what I'll do, I will clear all my cell executions. Right, so I'm going to clear all. I'm going to restart the runtime for 1. And I'm going to clear all cell output. If I do that, it doesn't hide. Okay, it doesn't really matter if I hide the output, but what I'll do, I'll run each block so you can see it happen again, right? So firstly, right, so I have here some general steps in the framework in which you could do machine learning. Now, this is not by definition of anything that's set in stone. It does change depending on your use case, and certain people leave out certain things, and some people mention it explicit, right? So I try to mention generally at a high level, not in too much detail, some general steps you could take that in which you could do machine learning, right? So the first thing is data collection. You need to gather your data, ensure that it's properly, it has proper labels, it's proper in terms of its features and so on. The second step would actually be taking that data now and ingesting that data into your system. So that could be like taking your Excel sheet with some data and using code to digest the sheet and get it into a form that's able to be manipulated or processed using Python in this case here, right? So then at this point now, your data could have missing information. So you need to find ways of now, filling that missing information and so on, and doing some cleaning as well. So, right. There's also a measure of determining or selecting now your measure of success. So in the case of the slides here, our measure of success here is going to be the distance between what we predicted versus what the actual observation was. There's the part now of what model you're going to use. You're going to use linear regression. You're going to use neural network and so on. That's up for debate as well. Then there's the issue now. Okay, we have the model, we have the data, we have the success measure. Let's go ahead and train the model now and see what results we get. Right? We're going to now evaluate the model in some particular way, and then we're going to make predictions now for the future. And then, it is like a whole loop here now. We're going to constantly improve the process, right? So the first cell I have here, right, is a cell that does imports, right? So we're going to import some particular libraries, and I have the libraries defined here and what they actually do. So NumPy is a particular language for numerical computing in Python. It supports large multidimensional arrays and matrices, along with a collection of functions to operate on these arrays, right? There's the issue of the pandas library, right? And it's, again, a next library written in Python for data manipulation and analysis, right? sklearn is a very popular library, and it's a free software library for machine learning in Python. So what it is actually is that there are a lot of machine learning algorithms, and sklearn actually implements, the core logic behind the algorithms for you. So it actually makes doing machine learning very easy, right? You don't have to go and look up on the algorithm for a neural network or logistic regression. It has it there in a function that you could just call, right? And there's also a very nice package called Seaborn, which is a library to visualize data, right? And it's based on our next library called matplotlib, but it makes visualization very simple and easy to understand, right? So now we're going to load our data set, right? So within the sklearn library, or a package there's actually a California housing data set there for you to use, right? So I'm going to run the code here, and I'm going to explain it line by line for you guys, right? So we're going to say from the data set library in the sklearn package, we're going to import the fetch California housing function, right? Then now we're going to call the function, which is going to return now our data set for us, right? So what I'm going to do now, that's going to be stored in the variable cal dataset, California dataset for short, and I'm going to just do print now cal dataset.describe. So it's going to describe for us now, some characteristics about the data, right? It's going to describe how much instances we have. We have about 20,000 instances, right? We have 8 attributes or 8 features. So for each instance or each row of information, we have, the median income for the block group for the house, the household age, which is the median household age in the block group. We're going to have the average number of rooms per household, the average number of bedrooms in the house, and so on. So every row, so again, we have 20,640 rows of data. Every row has this information here about the house, right? It says that there's no missing information, so that's good for us in this case here. And it says that the target variable, the value that you want to predict on, is the median house value for California districts, expressed in the hundreds of thousands of dollars. So your target variable is the price of the house and the median value of the house in 100K, right? And you have some more information here about the data set and where it was developed, how it was obtained, and so on. So we could kind of ignore this for now. So we're going to do now is take our data set and bring it into the pandas library. So again, pandas is a library that allows us to manipulate and do analysis. Manipulate and do analysis on our data. So we're going to be using that library a lot throughout, the lab, right? So what I'm going to do, I'm going to call PD, right? So again, we can refer to the pandas library in short by saying import pandas as PD. So PD allows us to refer in short to the pandas library. Same thing for NumPy and so on, and Seaborn, right? So I'm going to say PD.dataframe, It says, okay, this expects now some data and a list of the column names for the data. So in the first parameter, you're going to specify here a data, right? And that's conveniently said by saying cal dataset dot data, right? It's going to return an array. And now we're going to specify the columns for the data. So the data actually here has some names for each of the features. So if I say cal dataset dot feature names, we're going to get now the feature names for each of the features. So medink, house age, and so on. So what this is going to do now is construct a pandas data frame now with some data, as well as have labels for each of the fields of the data, right? So that's one thing here. So actually now what I'll do, I'll show it running here, right? And there's a pretty cool function in pandas. So I'll say now df.head. That allows us to say, okay, I want to look at the top 5 rows in our data frame, in our data, and see what it actually is. So I'm going to execute it here. So we see now that we have, okay, the first row, we have the median income as that, the housing, the age of the house, average number of rooms, and so on. The second row of data has all these things here, and so on. The third row, and so on, right? So I'm going to say now, so what I could do, I'll go on next block here, right? I could actually refer to a specific feature in the entire data set, right? So I could say df, and if I say open square brackets, and I say in quotes now, I could specify now, as it's seen here, any feature here. And if I say df longitude, if I run the cell, it's going to return to me, all longitudinal positions for each of the rows. So effectively, it's this entire row here, and not the rest, right? If I specify multiple rows, I can get latitude as well too. And return now a data frame now, latitude. Oops, that should be in double square brackets. That should be now a data frame now being returned with latitude as well as longitude. So you get that here now, right? So you can make it even more to your heart's desire, right? So if you say df now, you're going to get the entire thing, as you see there, right? So we have now, as you see here now, we have 20,000 and something rows and 8 columns of data, right? So we're okay there. Anybody confused so far? It's fine if you're confused, right? You could always go over and explain.
Just one question: the data that they have here, right? This was already set up from before.
Yeah, so it's available within the sklearn library. So you can see here now, I said sklearn.dataset. So that means now that this particular library has a set of datasets that you could use. But Google it here. So this is the documentation for the package, right? It's very much in detail. And if I go here, there's, you can see it here now. California housing data set. It's a regression problem. Hint. Here's a data set on label faces and so on. So it comes bundled with certain data sets by default that you could use. So that's very simple. I just use a default data set inside here for the machine learning problem we're going to try and solve, right?
Okay, understood.
Good. Where were we? Right. So now, right, what I could do as well with my pandas data frame, right? I could say df, I could say price is equal to cal dataset.target. So if you realize here, right, when I display my data frame here, it actually didn't have any feature called price. It has medium, income, and so on. It doesn't have price at all. So what I could actually do is add a new column to it, or add a new feature, and that feature now is going to be cal dataset.target. This here now is the median value, I think, for the house, right? So we're going to assign that now to df price, right? So now, before I had this number of rows and I had 8 columns now, a quick way to obtain the number of rows and columns by saying df.shape. So I have now one more column now, right? And if I go to here now, I do df.head, you'll see we have now everything here now plus the median price. Make sense? Right? So now, right, before I go ahead and do any kind of machine learning, what I should be doing is that I should check my data. I should see that, okay, is anything missing, right? So what I could do, there's this function here in Pandas called isAny. Again, if you Google it, let's just see what it is. isAny is a function that returns whether or not your data frame contains missing values. So it's a quick way to see if it's missing, right? So I'm saying df.isAny.any. So let's just go back and see what df.isAny does, right? It returns now for every single value, for every single feature, if it's missing or not. So the values here are false. Now, as you can see here, we can't manually inspect the 27,000 rows, right? It'd be good for us to kind of summarize the information. So by saying now .any, this means now if any row contains missing data, it's going to return true, right? So by doing this now, I'm going to break it down now and check it now and say, okay, if the median income had a missing value, it'll be true. And I say, okay, now I can go and investigate this and say, okay, I might want to remove that row with missing information, and so on. So luckily, because this is a very perfect data set, it was very clean, as you could say, it doesn't contain any missing information. So that means that we could go ahead and go a step further, right? There's a method in Pandas called df.describe. So with this now, what this would do, this would take all numerical features and derive for us the count, the mean value, standard deviation, min, max, and different percentiles. So the price now has a count of 20,640, which is expected. And the counts here are same for across the board because we have all values for all features here, right? So now we have the mean value. The mean price of our house is $200,000, right? The standard deviation between the prices actually are $1,150,000, and the maximum value for a house is $500,000. The minimum value is, I think, $10,000, I believe, and so on. We have latitude, longitude. We have these values here. So you understand what the df.describe function does, right? So now we have an idea of what's going on. So we have now, at this point now, a data set. It has features. It's effectively considered clean because there's no missing information. Now, let's go a step further now and try and visualize our data. So let's try and make now a sense of kind of what's going on. So we see it here, but let's try and get in a graphical form, right? So now, what I could do is use the Seaborn library, right? And I could do different types of plots. So if you hover over the function name here, SNS, again, refers to the Seaborn package. And if I say scatter plot, this allows us to construct a scatter plot based on some data that we have. Our data is going to be supplied by DF, which is our data frame. Our data points we're going to use, right? Our Y value is going to be latitude. Our X value on the graph is going to be longitude, right? And we're going to define what hue is shortly. So let me just remove hue, just for simplicity's sake right now. Right? So I'm going to run this here. So I'm going to get now, I should run that. Okay, so I'm going to get here now a nice simple graph of latitude and longitude coordinates plotted onto it. So I'm fine here. Now, where did this come from? So again, what this means here is that we're going to be using our Pandas data frame. And this means that we could use any feature inside our data frame to do plotting. I just chose in this case here to use latitude and longitude. So we see that here, that in df.head before, we actually have latitude defined here and longitude defined here. So that means we could reference it. Now what happens now if we just do this? Do you think this is going to work? If I type common L for the programmers in the group, is it going to work if I say latitude with a common L? It's not going to, right? Because there's no way latitude with a common L, sorry, is defined in my data set. It's defined with a capital L. So you need to be very careful of what you're specifying. So it says here that it can't interpret the value latitude. Makes sense, right? So we're going to go back now to put capital L, and it works, right? So we're good so far. Now, I'm going to re-include what I had before, something called hue. If you look at the documentation and it's scatter plot for what hue is, right? So what this means is that we're going to be plotting latitude and longitude coordinates with regard to the price. So what Seaborn is automatically going to do, say, okay, if the prices are low value, it's going to assign a different color to my point. If it's a high value, it might assign a different color to the point. Let's just see what happens. So let me just increase the size of the plot. I think it should be 14 on the X. Just make it 10 on the Y. And if I do over the graph, it should get bigger. I hope. Better, right? So what this is here now is the same graph we had initially, the same blue dots, but now we're gonna color the dots based on the price. So if it's based on the scale here, or the key, right? If it's a high price, it's more dark in color. And if it's a low price, it's a bit lighter in color, right? So we see in here that there are certain concentrations here where we have dark colors, I mean that there are expensive houses here. And then scattered throughout now, we have like much more cheaper houses. And then kind of close to the expensive houses are the medium houses in terms of cost, and so on. Makes sense, right? So we're good so far. So if you're okay so far, and you understand, what the scatterplot function does, it's going to take some data, or panel data frame. We're going to specify what the X and Y data point should be, and then we're going to color code it by the price, right? Simple there so far. So we're good. We can also do in Seaborn a line plot. Again, it's simply the same thing. We're going to pass now our data set, X and Y values, of what we want to plot, and then now call the line plot function within the Seaborn package. So I can run this here now, and we're going to get now a line plot of X being your house age, and then the price. So as your age, from what we can see here from our data, as the age of the house tends to increase, the price goes up a lot. So like this is for a very new house, it goes up highly. And as it gets a bit older, from about 3-4 years, all the way to about 40-50 years, it's kind of more or less stagnant. It's pretty much the same. And then now, for some weird reason, once it passes 50, it goes up. This could be that the house is actually a vintage house, and typically a vintage house might go for a higher price because of the rarity or whatever. Right? So that's probably could be why you have that reason for your data there. So again, with visualizing your data now, you could actually detect certain trends and see certain patterns and make investigations into it. Simply just by doing a describe here, you can't really see what's going on with the price too much across the board, right? But you could actually combine now house age and the price and say, okay, with a certain age of house, I expect a certain price, right? It's a histogram plot. This came out pretty bad because we have a lot of values, 20,000 values. And what happened here is that there's some houses, right, with average number of rooms being 140, as you can see here. So that's why it came out pretty bad. But typically, a histogram plot would look like this. Pretty much a bit more uniform and a bit cleaner. But because we have so much data points here, and because it's floating point, it isn't so nice, right? So we could do actually. So we're looking at now the average number of rooms in our house, right? Let's go back now to the df.head. So the average number of rooms here is a value here, is a floating point value. So what we could actually do is convert it to an integer, right? A simple way of doing that is saying, okay, we could say df average rooms converted. So this is a new feature we're going to add now, and it's going to be equal to now df average rooms, and we're going to set the type as integer. So what that's going to do now is convert now the number of rooms to an integer value. And now we're seeing here now we could do a count plot now, a next type of plot with now our data and the average number of rooms converted. So we've seen here now that there were a lot of houses with an average of 5 rooms, somewhere there. There were some houses a bit less with 4 rooms, and a lot less definitely with 62 rooms, and so on, right? We can also do a bar plot against the price now of the average number of rooms converted. I need to run this actually before I could display it. So we see now that for a room with average number of like say around 8, you're expecting the price to be between, you know, the black values here. Start on the end. So like between upper or 350 to about 400K, you're gonna expect a house with about 8 or 9 rooms to be that price, right? I think in the case of the last value here, it means that we have only one entry here with I think 141 rooms and $5 million, or sorry, $500,000. Makes sense, right? So if you're good so far, give me a 1. If you're not fine, you can specify what's giving you trouble, and we can treat with the issue. So if you're okay, give me a 1, and we can continue. Okay, good. So now we shifting now gears again. We're gonna go from the visualization aspect of it now to the more machine learning side of things now. So we have our data, we ensure that it's clean, we visualize aspects of it, made some inferences, made some analysis. Now we could go ahead now and try and do some machine learning. So before we get to machine learning, there's one thing we need to keep in mind, right? And I have a meme here, right? So there's a notion of something called train test splitting, right? And what it is that it's a method for us to evaluate the performance of a machine learning algorithm, right? So what it does, it effectively splits our data into 2 portions, one to actually train on and one that we could do testing on. So as specified in points 2 and 3 there, we can use the first portion to train the machine learning model and make it learn. And the remaining portion now is what we could use to evaluate to say, okay, I can see how good the model is going to perform on this new data, right? So what do you think is going to happen if we use the portion of data that was used for training as part of the evaluation? Anybody? What's going to happen there? So if I say 5 plus 5 is 10, 6 plus 6 is 12, you're going to get exactly 100% match, right? So you can't actually say, okay, I train my data on the sum of 5 and 5, 6 plus 6, and I could evaluate it now back on what it was trained on. It doesn't make sense, right? So what we need to do now is say, okay, given our data now, we need to split it up into a train portion and a test portion, or evaluation portion, as they say as well, right? And with the train portion, we're going to make the model learn. So, okay, given some information here about my house, which is this here, I say, okay, the price is going to be that. Given this information here now, the price is going to be that. And I'm going to feed that into the algorithm and make it learn. Now, for the test now, what we could say, okay, let's just say for a very simple example here, let's just do df.head 20. Right? So what it says here, let's picture that this was the entire data set, right? What I'm going to do with train test is to say, okay, entries 1 to 14, I'm going to say I'm going to use you for training, right? And entries 15 to 19, I'm going to use you now for evaluation. So the model now has never learned or has never seen this information here, this latter 5 rows. And it's going to now say, okay, given this information here, I now could predict the price and compare it now back to the actual price. And then now we can determine all the loss based on that. Make sense? So in the example with the slides here, I simplified it a bit by saying, okay, we have only one feature, the area of the house. And we're going to predict now the price of the house. But in this case now, we have multiple features now, right? So it's a bit more hard to represent multiple features on a graph. So that's why I only had a 1, right? What we're going to do now is say, okay, given these multiple sort of features now, I can say, okay, now I want to learn the price or predict the price, right? So we're good so far.
One question.
Sure.
So this seems to be very dependent. Is it very dependent on the data that you split it? So if you split 1/2 for the testing and split 1/2 for the training,
yeah,
how do you know you chose the optimal part to train on?
Right. So there's no actual way. Okay, so if you're using the train test split method, there's no way of saying, okay, we're not sure. We don't know for sure exactly what's going to happen in the future.
Mm-hmm.
So I didn't put it here, but now that I brought it up, I can put it to the end here now. There's the issue or the mention of something called cross-validation. Right, so what I'll do, I'll leave it here for you guys. So it's for further consideration, right?
Okay.
Let's just Google it quickly. It's a nice image here. I use this for a class actually. Right. So, right. So again, let's ignore iterations 2, 3, and k. We have now our data here, which spans all data, the arrow here, right, as that there. Then now, as we said before, you have a certain portion allocated for testing or evaluation, and there's a certain portion allocated for training, right? So you're saying here now, okay, there's a point now that our training data, our model might have actually done on this data here. It's impossible, right? Because we can't do it.
Mm-hmm.
So what we could do, this is a technique called cross-validation. What it does, it allows us to break up our data into different segments, right? So let's just say now, in this case here, we're going to use 3/4 of our data for training and 1/4 for testing. So the first iteration here, we take the first quarter, use it for testing, and the remainder for training. In the second iteration, right, we're going to take the second quarter now and use that for testing. And the ones that are highlighted here in the darker colors are going to be used for training. So that way, we're actually maintaining 75% training, 25% test. But we're going to compare now, or we're going to use now every single segment of our data for testing. So that way now, we could actually get a more real world idea of the performance. Because now, we're effectively going to test now on every single segment of our data in some form or not, in some scenario here. And what we could do, given that we train here, and we test here, and we get the performance here, the loss. We get the loss here. We get the loss here, and the loss here. We can now simply say, okay, this is the average loss now across my entire data set for all my data. And say, okay, now I know that my model now has an average loss of whatever value over the entire data set now, which on average. So that there now is a better way is a better way than saying, okay, let's just only use train test split.
Oh, okay.
Right?
All right.
Yeah, so there's a good point you made there actually. So I have it here at the end so you could actually Google it and reference it. But just for simplicity purposes here, I didn't put it in, right?
All right.
Okay, cool. Okay, so before we could go towards now doing machine learning, so let's just go back to the meme now, right? So with the meme, what I wanted to say is that, okay, if I take my model on training data, it's going to look good, right? Perfect. But on test data now, that data that the model has never seen now is a whole different scenario. It's a whole different bunch of problems now. So that's why anybody could claim 100% accuracy. But it's what parts of the data they use for the evaluation part that's important. If you use the evaluation data set as part of your training set, you're going to end up with the first part here. Best performance, you're good. If you use now, it's not going to happen all the time, but in some cases now, portion of your data set for evaluation that wasn't in your training data now, it could have bad performance. You never know. So you're saying here now, okay, it's not so ideal now, and it's not so easy now to get your performance to be 100%, right? So we're good so far, right? So we understand the difference between training and testing. We understand why we do it, and now we understand actually now train, test, split, and cross-validation, right? So one step further now. So before we can actually do the machine learning, we need to do the actual splitting. Now, before we can do the actual splitting, we need to actually define what's going to be used for input and what's going to be used for output, right? Again, input in this case here is my features, so the size of the house, the area of the house, number of persons in the house, and so on. Output is going to be the price, and then the rules is what the model is going to learn. Right? So going again. So I'm going to say now X or big X here is going to be pandas data frame with the medium income, the house age, and so on, right? And I'm going to do a drop now on the number of rooms converted now and the price. So I could never have my machine learning model learn with the price. It doesn't make sense, right? Because I can't have my input being the price. The output should be the price, right? So I'm going to say now, I'm going to drop the columns this here as well as price. So X now is now our next pandas data frame with these features I've highlighted here now. It's not going to have the price or the average number of rooms converted. That's what X is going to contain. Y now is going to contain the price. So the price now is in a separate data frame by itself, right? Now, we can use the train test split function from the sklearn library. So what it does is defined here. I'm going to say train test split. I'm going to pass in X, which is my input values, Y, which is my target value or my output value, and I'm going to say test size is 0.2. So this means now that out of all data points, my test data set is going to be this number of rows, and my train data set is going to be this number of rows. And you must have train and test be the same number of columns as well, right? So that's X train and X test. So X train is for the model learning part, and Y train is for the model learning, right? X test and Y test now is going to be for the evaluation part. So we have here now X train.shape, X test.shape, and we see now that X train.shape and Y train.shape must have the same number of rows. If there was a difference in number of rows, it would never work out for the model to learn. So for every entry of X information, there's an output of Y information, and so on, right? Similarly, for the testing scenario or the evaluation scenario, we're going to have the same number of rows and columns, 4128, and then 4128 rows. But in this case here, we have X test, which is one value, which is the price. So we have that there now. So now when we run this now, we're going to have X train, X test, Y train, Y test. I need to run the cell first. I'm going to run this, so we're good now. So now we're at the point now where we can actually use linear regression, right? So I mentioned before, we need to select a metric, right? So in the slides here, we use very simply in our abstract scenario, we use the sum of the square between the observations and the predictions. So we're good so far. Now, there isn't really that loss function defined in the library. Here's a bit more complex. What they have here is something called the mean squared error. All right, so that is the square error between each data point and the actual value and the predicted value and the mean of it now. So it's just now, I believe, where the average being taken into consideration, right? So that's all you need to know. So now we're going to import the linear regression model. We're going to import now the error function or the loss function we're going to use, right? Now we're going to train the linear regression model. So we're going to define it here, and we're going to do something called fit. So fit now says, okay, I want you to learn with my training data. So I'm going to pass now X train and Y train it. That there now is going to make the model learn, right? So I'm going to run this here now. That there now has instantiated the model and made the model learn on X train and Y train. So now it knows something now. It constructed the rules based on my training data now, right? So now, based on that now, I was talking about the issue of interpreting the model. So with linear regression, you could actually investigate the coefficients for each value, right? And what the coefficients tell you is that whether there's a positive or negative relationship between each variable here and the dependent variable. The dependent variable is your price or the Y value. So it's saying here that there's somewhat of a positive correlation between, the median income and the price. So that's what this is defined as here, right? So now let's try and evaluate how well the model is going to perform. So we have that model. It has been learned, has been trained, right? And we're going to say, okay, now I have a little bit some data. I want to try and see how well now my test data is going to perform on it. So now I'm going to say, okay, same learn model, and I'm going to say dot predict now. I'm going to do a prediction now on my X test now. The data that the model has never seen before in its life. And that result now is going to be stored in Y test predictions. I'm going to say now mean squared error. I'm going to pass in now my actual values and my predicted values now. And then now it's going to compute now the mean square error for me. I'm also going to compute now the root mean square error, which is the square root now of the mean square error. So I'm going to run this now. I'm saying now that the mean square error is 0.53. So that means here that on average, the distance between my prediction and my actual values are $500,000 or around $53,000. That's what we're saying here. Does that make sense to you guys?
Yeah.
Okay, good. So that pretty much there more or less is the intro to linear regression. So things of further consideration now, right? And this really is stuff I can't really explain too much, because to know why we need to go and consider it, we need to understand linear regression in detail, right? So if I go for linear, right, say pseudocode, for example, right? You need to have a fair understanding of maths and statistics to understand what's going on, right? It's not even explained properly here. Let's see what this thing says. Right, so again, you see the issue of having a cost function or a loss function. There's the issue of implementing gradient descent, right? And all of this business here going on. So, and a lot of more theoretical understandings you need to know from the ground up, right? So what I did is that I tried to kind of abstract out what essentially each thing means. So, with a loss function, that's what it does. With the gradient descent, you know what it does. You know what in algebra and a general sense, sorry, how if you have a machine learning model here with the red line, you could compute the error or the loss by comparing the distance between, that there, right? There are different ways of constructing or computing the error, right? So thanks for further consideration now. Effect of the range of the features. So let's go back up to where we have the df.describe. So we had here now, min and max for each feature. Right? So we're saying here now that for the median income, the min is 0.499, the max is that. We're saying that for the population now, the min is 3, but look at this now, the max is 35,000. Now, I'll explain this very briefly, right? Is that if you have data like this, and it is dependent on the model, right? So in terms of linear regression, if you have data like this and you pass it through linear regression, it's not going to be ideal, because what's going to happen, right? So what linear regression tries to do, it tries to assign a weighting or an importance factor to each feature here. Now, if each feature here isn't scaled properly, what's going to happen? You might have a sense of a false signal being applied now to the population or the median income features. Makes sense, right? So what should be done here? We should actually try and scale now, or modify the scale in which each of these features here should be. So what we should try and do is try and actually standardize the scale, make everything between 0 and 1, and see what happens there. And that now is going to give us one way of trying to improve the performance. But again, to understand why, I try to explain in a very brief scenario, but to understand why, you need to understand, the maths behind the modeling and all the code and so on, right? Next thing we could do actually is remove certain data points, right? So what happens now if now I realize that I don't want to consider this house for the 141 rooms? What's going to happen? Should I remove it? Should I keep it? So all these things now come into consideration. Should I actually remove houses where the number of rooms is less than 3? You don't know. So all these things now come into consideration as to how to modify a data set now. And it gets pretty much in detail. Now, with the aspect of linear regression, there are also variants of linear regression. So if you go on the link here, it'll be provided in the slides. There's also ridge and lasso regression, right? And what they do, they actually have a modification to the learning or the cost function applied here. So it's even more complex, and you're seeing what's kind of going on here now. So again, we don't really have the time or the background necessary to go and explain it, but you could start, right? And well, you have now cross-validation. We explained that before, but you could Google it. I'll actually include a nice link for you on cross-validation before I send out the slides, so you have an idea what's going on. So now, what we could do, if you want to go explore some more, we could try and scale the features now before applying linear regression. We could apply a ridge and lasso regression and see what the mean square error is. And that, could make this thing so in-depth and so much more in detail. And, but could be a few hundred blocks of code long very easily, right? So that now kind of brings us there to the end of the formal, learning session. The link is provided, and it'll be there forever. So it's shared from my Google account, so you have access to it unless I delete it. So I won't delete it, right? So yeah, that's pretty much it there for this part of the presentation. And let's kind of go on to the wrap up now, right? So in this section here, we explain all the concepts. Where do I start, right? And next meme, some of you are doing computer science, some of you are doing maths. Machine learning is actually a blend between the two, as you can see. So you need to have a strong computer science background, ideally, and a strong mathematical background. In my case, actually, when I started off, I had a strong CS background, but my maths background was a bit weak. So there were some courses I needed to do, some information I needed to read, and so on to get the maths background a bit up, right? So again, to be a good data scientist, a good machine learning engineer, and so on, you need to have a good understanding of algorithms and maths, very strong understanding, right? Now, where do I start, right? So there's Kaggle, Google Kaggle. It's a free data science platform that you could learn and do questions and so on. So I have a Kaggle account. I don't do much on it actually, but there is the California prices data set listed here. I think there's more data here actually, and there's a notebook that somebody actually has here where they did, a set of stuff, right? And their code actually is there online. So you can learn and see what they did and do different things. I just did some very basic stuff for you guys, right? So you can see here now, the correlations for all these things here and different types of plots. This is a heat map and so on of the things, right? And I think if you go back, if I go on notebook, for this data set, there were over a few hundred notebooks for it. So if I go on notebooks, right, so if I go on the code here, you actually see that there are over 300 notebooks where people did certain work for it, and you could filter. So like, I believe you could filter by the most votes. So this person actually did some good work based on the avatar. She did some good work analyzing this data. So you could take a look and see she did data imputation, because I think in this version of the data, some was actually missing. So like the median income here, I think was missing in some regards here, right? So good to know, like very nice plots, based on what was going on. And this is actually a very nice notebook. So what I'll do, I'll actually include, I won't include this because it does stuff with Bayesian regression that's even more complex than linear regression. So I can't include everything, right? But you get an idea of what's possible and what could be done, right? So again, this platform is very useful. Next, so Professor Hussein and a colleague in Zamam of mine, they develop our website, right? And for those of you who are interested in machine learning and data science, they recommend these courses to kind of start off on. So if you're not strong in Python, there's a Python course. You can contact Zamam if you want additional information. I think his email is here. Probs and Stats is a nice course on, I think, EDX. That's actually from MIT. It's based on MIT work, right? There's a course on linear algebra, I think also based on Texas, one of the Texas universities, a very good course, right? So good courses to start your foundation off. There's a nice website for those of you who don't know Python. I find this is very intuitive and very user-friendly. So if I wanted to learn variables in Python, I could click it, minus the add. It gives you a video, and then you could actually, they explain some stuff, and then you could actually go on to some code, I think, somewhere down the line here with our lab. Somewhere to the end. I think if I click this, no, it copies the code. You could copy the code, and I think there should be some way to run the code. So what I could actually do is actually just type Python 9, and probably the first one here. The same website has actual compiler, so you could copy and paste the code and see what's going on with, if you copy this here, what's going to happen with your output and modify it and so on online. You could also install the Python executable for Windows, and it's very easy, so not hard to do, right? This course is a very amazing course. It's very popular, and it came out a few years ago, a few years well, but it has, a lot of the foundations, that are required to understand linear regression in detail, clustering and so on. It does the work excellently, right? Now, the only thing with the course is that it's in a language called Octave, right? So if you're with MATLAB and Octave are quite similar, and we don't really use it much in terms of production with machine learning. I mean, there are some labs and places that use it, but in terms of my experience, Python is more popular, right? So there's this repo here on GitHub, right, that actually contains the assignments for the course, but done in a Python fashion. So what it does, once you clone this Git repo, you could actually do the exercises for the course in Python and submit it through the Git repo here. It's explained here how to do it and so on, right? So it makes it a bit more modernized for the Python age, right? So you actually have to go on an Octave. Very useful link, I find. Very nice book as well too. Hands-on machine learning with sklearn, the same package library we had before, and some additional libraries as well for doing learning more neural network stuff, right? It's very good, very detailed, and explains things from the ground up as well, right? This was a book recommended by, I think, Stefan Hussein. He is actually ex-Google employee. He studied at the department, actually. I think if you Google him, you might see him. Actually, let's go to his LinkedIn, actually. He's a machine learning engineer at this company here. He previously worked at Google and Twitter, and he studied at DCIT, actually. He has his BSc at UV from 2011 to 2014. So that was his GPA, as you could see. So just a note, from UV actually have gone on to do stuff at Google and these fancy companies away, right? So that brings us yet to the pretty much more or less end of it. I have a slide here, just a quote on doing things that if you're interested in, do something that you like, that you're passionate about. Don't make it because of the money or because you hear your best friend doing it. Do it because you actually like it, right? And things will kind of work out if you do that way. So again, make sure that whatever you're going to do in your career, make sure that you enjoy it, right? And that you're passionate about it, and things should fall into line, right? Yeah, that brings me to more or less the end of my presentation. So again, I'll share the slides with Jeremiah, as well as the notebook link will be included in these slides as well. So that brings me more or less to the end of my presentation today.